In this lecture, we'll start studying random walks on networks. Let me start sharing my screen. So we'll begin by introducing our model for a random walk. G is going to denote a connected undirected graph with vertex set V and edge set E. And xt is going to denote the random walk. So time is going to be continuous. T takes values in the positive reals. Xt denotes the position of the random walk at time t, and the random walk moves from one vertex of the graph to another. So the state space of this Markov process, the state space of this process is the vertex set V, and we define the process to be Markovian with generator minus L, where L is the Laplacian of the graph. Okay, so this is at the moment a somewhat abstract description of the random walk, and we'll see what this means in just a moment. Okay, so it's a continuous time process. It's Markovian, and we have specified the generator or the rate matrix, the infinitesimal generator of this Markov process. Okay, so firstly, what's the Laplacian? Recall that it was defined as the diagonal matrix of the vertex degrees minus the adjacency matrix of the graph. A is the adjacency matrix. D is diagonal with the node degrees along the diagonal. Okay. So the transition rates we define to be given by minus L. The generator is minus L. So that's the adjacency matrix minus the degree matrix. So the adjacency matrix, the VWth element of the adjacency matrix is 1 if there's an edge and 0 if there's no edge. And along the diagonal, we have minus the degrees. So this is the rate matrix. And let's check that it is a valid rate matrix first. So for that, two things have to be true. The off-diagonal elements have to be non-negative, and that's true. The off-diagonal elements are non-negative. And also, all the row sums have to be 0. And you can check that the row sum is 0 because the V diagonal element is minus the degree, and the row sum is the number of ones along the row. It's the number of edges from V to some other vertex W, and the number of edges is defined as the degree. Okay, so the row sums are 0. So minus the Laplacian is a valid rate matrix or generator of a Markov process. Okay, and intuitively, how do we think of this Markov process? So what do the rates tell us? So earlier, we looked at various examples where you had a verbal description of the process and you had to write down the generator matrix. So now you are given the generator matrix. Can you interpret it and say what the Markov process is? Okay, and this is what it is. So the rate gives you the probability of a transition in some very, in an infinitesimal time interval delta. So the probability in a very small time interval delta, you move from V to W, the random walk moves from V to W is 1 times delta. It's just delta. Okay. And the diagonal term gives you the total jump rate from a state of the Markov chain. Here, the state is the vertex. So what it says is that on reaching vertex V, the random walk spends an exponential time there, a random time with an exponential distribution. The parameter of the exponential is this minus QVV. It's minus the diagonal term, so it's exponential with a positive parameter, as it should be, which is the degree of the vertex. So the amount of time you spend at a vertex is exponential with parameter equal to the degree and mean equal to 1 over the degree. And after this random time, from state V, you move to some other state W. What's the probability that you move to a particular state W? That's proportional to the rate, and it should be normalized to be a probability. So here the rates are all 1, and that says you are equally likely to move to any neighbor W of V. Okay, there are no preferred neighbors. You're equally likely to move to any of them. And the probability is QVW, which is this, over minus QVV. So 1 over degree of V is the probability that you move from V to W. And that's the Markov process. An equivalent way to think about it is to say that, okay, so the transition rates are given by these off-diagonal terms. So you associate independent exponential random variables with each of the possible transitions. So for each edge VW going out of V, you put an exponential 1 random variable on that edge, independent for different edges. And then you look at which of these random variables takes the smallest value. So you are starting these random exponential clocks on each of the edges, and you see which clock rings first. And from a homework problem in your first or second homework, there are 2 things you showed. You showed that the minimum of independent exponentials is exponential with the sum of the rates. So the rates are all 1. There are degree V of them. The sum of the rates gives degree V. So you have the total rate of so the time until leaving node V, until one of these clock rings, is exponential with parameter degree of V. So that's the distribution of the minimum of the independent exponentials. You also showed, okay, so which of these random variables takes the minimum value? That's proportional to the rate of the corresponding exponential. And here the rates are all the same. So each of these edges is equally likely to be the one attaining the minimum value. And then you move along the clock which ran first. So you move along the edge, the exponential on which took the minimum value. And so you are equally likely to move along each edge. Okay. So these are 2 equivalent ways of thinking about a continuous time Markov chain, and you should be very comfortable moving between these equivalent descriptions. So one description puts the clocks on the states and says the clock on the state rings after a random exp minus QVV random time. And when the clock rings, you take the transition from V to W with probability QVW divided by minus QVV. So that's one description. Another description puts the clocks not on the states, but on the transitions. So there's an exponential QVW clock on each possible transition VW. And when you are in state V, you take the minimum of these exponentials. And at that time, the time corresponds to the minimum of these exponentials. And at that time, you take the transition which attained the minimum. And that's the other description of the Markov process. Okay, so I just want to remind you that that's a statement about general Markov processes. You should be very comfortable with those 2 descriptions, equivalent descriptions, both in general and in specific examples like the random walk. So take your time to make sure that you fully understand the model before we go on to analyze it. Okay, so if you're completely comfortable with the description of this Markov process, the random walk, and this is, let me emphasize, this is just one way of defining a random walk on a graph. There are other equally natural ways of doing it. For instance, you could have rate 1 at the vertex and 1 over degree V along the edges. That gives you a different generator matrix, but that's also natural, and you could study that instead. We've chosen to study this one. So for us, the generator matrix, the infinitesimal generator, is minus the Laplacian. Okay. Okay. Okay, so the first thing we might want to ask about this Markov process is what's its invariant distribution and how many does it have? Now, we assume that the graph is connected, and an immediate implication of this is that the Markov process, the random walk, is irreducible. If the graph is connected, it's possible to go from any vertex to any other vertex. And the vertices are the states. So this says that every state is accessible from every other state. That's the definition of irreducibility. Every pair of states communicates. Okay, since the Markov chain is irreducible, it has a unique invariant distribution. The existence is because it's a finite state space. So there is a unique invariant distribution pi for this Markov chain. Can we calculate it? We can. It's easy to do this, and there are two ways to do this. So one way is to solve the local balance equations, also known as the detailed balance equations. And I'm going to leave it to you to write down and solve these. Do it for yourselves just to become comfortable with it. It's good practice. And instead here, we'll solve the global balance equations. So let's recall these. These are the equations pi times q, where q is the generator matrix, is the zero vector. Just a quick remark about convention. Vectors will be column vectors unless otherwise specified. So 0 is a column vector, 0 transpose is a row vector. Probability distributions are a bit special. They are vectors on the state space, but by default, probability distributions are always taken to be row vectors. And so pi is a row vector, and pi times L is a row vector, and it's equal to this row vector. Okay, so reminder about notation. Mostly vectors are column vectors by default, unless they are probability distributions, in which case they are row vectors by default. Okay, so I said pi times q is 0, and I've written something else here, and that's because L is minus q, and that doesn't change the equations. Minus 0 is 0. Okay, so these are the global balance equations. Let's solve them. We already saw that if you multiply L by the all one column vector, you get the vector of all zeros. This is because the row sums of the Laplacian matrix are 0, and multiplying by the all one column vector is the same as computing the row sums. So they are all 0. In addition, the matrix L is symmetric because the graph is undirected. So we can take the transpose of this equation, and we get 1 transpose L is 0 transpose. So the all one row vector solves the global balance equations. Does that make the all one row vector the invariant distribution? Not quite, because this is not a probability distribution. If you add it up, it adds up to n, the total number of vertices, rather than to 1. But that's not a big deal. We can simply normalize it to add up to 1. So we do that by dividing by n, the total number of vertices, and then it adds up to 1. And that's an invariant distribution. That's one invariant distribution. And we also saw it's unique, so it's the only invariant distribution. Okay. So the uniform distribution on the vertex set is invariant. In the long run, the Markov chain is equally likely to be at any vertex. That's what this invariant distribution is telling us. Okay, so what can we say about the long-term behavior? I already said one thing, it spends in the long run an equal fraction of time at every vertex. But in fact, we can say a bit more. So if we denote by Pt the probability distribution of the Markov chain at time t, meaning that its vth element is the probability that the random walk is at vertex v at time t. So this is a sequence of, or a family of distributions, probability distributions on the vertex at v, indexed by time. So you start in some distribution. I tell you what p at time 0 is, and at any later time, you have some other distribution. So the probability distribution evolves over time. And what happens in the long run? So what does it, do these distributions tend towards something as t gets large? And we know the answer to that. They tend towards the invariant distribution pi. And this follows from the ergodic theorem for Markov chains and the fact that this Markov process is irreducible. Okay, if it were not irreducible, then it decomposes into subsets. So if the graph is not connected, it's in pieces, and depending on which piece you start in, you might converge to different things on that particular piece. But by the assumption that the graph is connected and the Markov process is irreducible, there's a unique invariant distribution pi, and starting from any initial condition, we get closer and closer to this invariant distribution as t gets large. That's the ergodic theorem. Okay, and so the question we are going to be interested in our study of random walks is how quickly does this happen? Okay, so how long do we have to wait until pt is very close to pi, as close as we would like it to be? Okay, to answer this question, we need some notion of what does close mean. So when I say pt converges to pi, in what sense, in what measure of distance does it converge, and okay, and how quickly? So we need some measure of distance between probability distributions. How close or how similar are two probability distributions? We saw already that probability distributions are vectors on the state space, are row vectors. So we could just use Euclidean distance. That would be a perfectly reasonable choice. In fact, when studying probability distributions, a different measure of distance is more common. And so what we are going to do next is introduce that measure of distance and look at some of its properties and how it's related to Euclidean distance. Okay, and this measure is known as total variation distance. So let's start by defining it. So suppose that P and Q are two different probability distributions on some finite set S. So you can think of them as row vectors indexed by the elements of S, or you can think of them as probability mass functions on S. And then the total variation distance between them is defined as follows. So we'll denote it by D for distance, subscript total variation. Between P and Q, it's defined as the maximum over all subsets P of S, including the empty set and the whole space, P of B minus Q of B. So P of B is the total probability of the set B, obtained by adding up the probabilities of each single element set within it, or by adding up the mass functions, the masses of all the elements within B, and similarly for Q. Okay, so this is the definition of distance. Take a moment to make sure you understand this. Okay, you might notice one thing immediately. So the order in which I write P and Q here seems to matter. The definition doesn't look symmetric in P and Q. In fact, it turns out it is symmetric, and we'll show that in a bit. And also this DTV satisfies some other notions that we typically associate with distances. So if you know what the definition of a metric is, you can check that the total variation distance satisfies all the properties of a metric. If you don't worry about it. It's not terribly important. There are other measures of dissimilarities between probability distributions which are not metrics. So relative entropy, which some of you may have seen, is not a metric, and it's not important that we should only work with metrics, but it so happens that total variation distance is a metric. Okay, so here's a concrete example. So let's take this 4-element set. P is the probability distribution which assigns probability 0.4 to 1, 0.3 to 2, 0.2 and 0.1, whereas Q is the uniform distribution on all 4 possibilities. Okay, so here are 2 probability distributions on this finite set, and what's the total variation distance between them? Okay, if we go to the definition, then we need to write down all possible subsets of S, calculate P of B and Q of B, take the difference and take the maximum. And how many such subsets are there? For a 4-element set, there are 2 to the 4 subsets. So in principle, we have to do this calculation for all 16 subsets and take the maximum. But hopefully, if you think about it a little bit, you can see intuitively that that's not true. That we don't have to do this. You should intuitively be able to see which set attains the maximum here. So let's start with the empty set. For the empty set, P of the empty set is 0, Q is 0, the difference is 0. And let's think about what element can we add into the set B to make this difference get bigger. So if we add the first element, we add 0.4 to P, B, 0.25 to QB, so the difference increases from 0 to 0.15. So it makes sense to include the first element. Similarly, we can add the second element as well, and it increases by another 0.05. And then if we add the third element, that adds more to Q than to P, and so it decreases this difference, so we don't want to add it, etc. So thinking about it this way, hopefully you can convince yourselves that the maximum is attained by this set. So we should take B to be just the set consisting of elements 1 and 2, then P of B is 0.7, P of Q is 0.5, the difference is 0.2, and that's the biggest it can be. Okay, so I hope this example is completely clear. It's also worth remarking that we have defined this for finite sets, but in fact, you can see that there's nothing in this definition which makes us restrict to finite sets. The definition works perfectly well for countable or uncountable sets. So indeed, total variation distance can be defined in general, even for continuous distributions, in exactly the same way as the maximum overall subsets of PB minus QB. Okay, and we'll remark on this again later when we give a slightly different formula for the total variation distance, which doesn't involve a maximization. Okay, so now let's look at some properties of this distance measure we defined. So the first thing to notice is if you fix a subset B of S and look at this difference PB minus QB, then that's the same as Q of B complement minus P of B complement. Why is that? P of B is just 1 minus P of B complement because B and B complement are disjoint or mutually exclusive sets whose union is all of S. So PB plus B complement adds up to 1. And similarly for Q. So PB is 1 minus PB complement, same for QB. The ones cancel, and this is what you're left with. So this is true for any subset. So the total variation distance, which is the maximum of PB minus QB, is also the maximum over all subsets of QB complement minus PB complement. So we are taking the maximum over the complement of all possible subsets. That's the same as taking the maximum over all possible subsets. Okay, so we could just as well have written max of B of L, B subset of S of this. And now you can see that indeed the definition is symmetric. Okay, so the total variation distance between P and Q is the same as that between Q and P. And as we saw in the example, the maximum is attained by taking all those elements X for which the mass function at X is at least as of P at X is at least as big as for Q at X. And from this, we can write the total variation distance. So this is a set which attains the maximum. So it's PA minus QA. And as we saw, this is the same as QA complement minus PA complement. So if we add the same thing twice, we divide by half, we get the same total. And so that's half the sum over, now PA is the sum over X and A of PX and minus QA. And similarly, in X complement, we are subtracting QX minus PX. And A was defined as the set where this difference was non-negative, and on A complement, the reverse difference is non-negative. So we can put absolute values around these sums. And then we just get half the sum over X in A as well as in A complement of the absolute value of PX minus QX. And so that's the sum over all elements in S. Okay. Now this sum over X in S of Px minus Qx, the sum of the absolute value of the differences, is called the L1 distance between P and Q, between the vectors P and Q. Okay, so it's denoted this way. If you want to visualize it, if you represent P and Q by their coordinates on in Rn, then P is some location in Rn, Q is some location in Rn. The Euclidean distance is the length of the straight line joining P and Q. The L1 distance, to think of the L1 distance, it's easiest to visualize in 2 dimensions. Think of a rectangular street grid, and P and Q are 2 addresses on this rectangular grid. So you can only move along the streets vertically or horizontally. And then the L1 distance is the distance you have to travel along these streets to get from P to Q. So it's also called the Manhattan distance because Manhattan has this rectangular street grid. Unlike British cities. So that's another name for the L1 distance. Okay, so the total variation distance is really the same as the L1 distance between these vectors rather than the Euclidean distance, and it's up to a scaling factor of half. Okay, and I've just repeated the same thing for a vector x. The sum of its absolute values is called the L1 norm of x. And the L1 distance is just the L1 norm of the difference between the two vectors. Just as the Euclidean distance is the Euclidean norm of the difference between the two vectors. Okay, so that concludes this lecture. So what we did was to introduce a Markov chain model for a random walk on a graph. We noted that the probability distributions of this random walk, of the location of the random walk at time t, should converge to the invariant distribution if we are talking about connected graphs. And then we introduced a measure of distance between probability distributions in order to quantify the notion of convergence, quantify the notion of distance. And then using this quantification, we can talk next time about how quickly this convergence happens. Okay, so I'll stop recording here.